Welcome back. I want to talk a little bit about data models as a run-up to talking about databases over the next couple of segments. So this is a data science course, so we know we have data. So the first question to ask is just, where is this stored? How do we store data? And so one way of interpreting this question is just to talk about technology, right? So what technology do we use? Well, we use magnetic media, and we might use solid-state drives more recently, right? And so both of these have the property that they persist even when the power goes off. The data is safe even when the power is not on. Okay, so non-volatile storage, right? And so a lot of the work in databases is all about how to work with data that's stored on these non-volatile storage media. But another way of interpreting the question is a little different, a little more of the logical way we store it, the organization of the data. And so we might ask, one way of interpreting this question is, what is the data model we're using? Okay, so it's not just bits on a disk or bits in a file. What do we do? Well, in your personal computer, or maybe in your work computer, you might store data sort of hierarchically, arranged in these kind of nested folders, right? That's one organization of data, and so the data model here is kind of tree-like. Another way is rows and columns, and this is what we'll talk a lot about in this course, right? So in this case, it's an ASCII file, and these are hits from a biological database, matches in a biological database for a particular sequence. And of course, you might have spreadsheets that are a little funny, right? Maybe they look a little bit like rows and columns, but maybe they don't. So here's sort of an embedded table within a spreadsheet and so on. So you need to the idea is to think about what data model is being applied whenever you think about data, right? And so it could be a tree, it could be a table, it could be something, a grid like this, unstructured, or it could be a graph, and we'll talk a little bit about that in the future. All right, so in general, what is a data model? Well, there's going to be three components that you should remember. All right, one is that there's going to be some notion of a structure, right? So in the case of tables, it's rows and columns. There's going to be some notion of constraints. What are the legal structures you're allowed to create? So for example, typically if you think about a tabular data model, you won't have all the rows will have the exact same number of columns, right? This is sort of a constraint. You might also have more constraints on the values themselves, such as, this field must be this column, every value in this column is an integer. And you could even have other kinds of more semantic constraints, such as every column in this, or every value in this column must be within a certain range of numbers because it represents, say, days of the year. Okay. And then the third one is the operations. And so this is sometimes thought of as independent of these three, but I really like to call the data model all three of these things. The structures, the constraints to define valid structures, valid instantiations of these structures, and then the operations you can actually, that these structures support. Okay. So let's see some examples. So your structures might be, as we mentioned, your rows and columns, nodes and edges if it's a graph model. Key value pairs has been popular with the NoSQL movement. Just a sequence of bytes, that might be the structures you have if you're just working with bare files. And then the constraints you might imagine are, all rows have the same number of columns as I mentioned, all values in one column is of the same type. For a hierarchical view, you might have a child cannot have two parents, right? So this would define, for example, one file cannot be in two folders at the same time in your data model of your file system. Okay. And then the operations that are supported. Well, maybe you can look up the value given a key X. In these key value pair data models, that's one of the primary operations. Is if I give you the key, you give me back the value. For a tabular data model, you might say, well, find me all the rows where a particular column has a particular value. In this case, a column last name is equal to the value Jordan. Okay. And with a file, there's not too many operations you can think about. It's essentially get the next in bytes, move to another position within the file, and then you can open and close the file, and that's about all the operations that are supported. Okay, so I think in any case you see data, especially on non-volatile storage, you can think about what operations are supported, what constraints there are over the structure, and so on, and this gives you an idea of the data model. All right, so what is a database? Well, one definition that I think is pretty adequate is this one, which is a collection of information organized to afford efficient retrieval. Right? So this is a pretty general definition. It doesn't say anything about tables, doesn't say anything about relations. So when you think about database, don't necessarily assume relational database. It's perfectly adequate to talk about a database that has nothing to do with relations. All right, but it is not just a pile of data either. It's organized to afford efficient retrieval. All right. So another view of a database is this idea of a schema. And so Jim Gray, in this Fourth Paradigm book that I've that we talked about in the eScience segment a little bit ago, has this quote: "When people use the word database, fundamentally what they are saying is the data should be self-describing and it should have a schema." That's really all the word database means. And so this goes back to this notion of a data model, right? There's a structure there, and in fact, and some constraints, and some operations, and all three of these are things you can intuit by looking at the data itself. It needs to be self-describing, right? So if I have, if I have a table, if I have a file of data that's organized into rows and columns, somewhere I'm able to inspect which columns it has and how many rows there are and so on, right? I need to be able to understand how to read this data just by looking at the data itself. And so in a database, for example, there'll be a catalog. There will be an explicit schema. So having this idea that the word database is synonymous with self-describing data, data equipped with a schema, that's a pretty common view, and it's an important one to keep in mind as we go through this course. So let me give you another view of a database, motivated by this question: why would I want one in the first place? Why would I want a database? What problem do they solve? Well, there's maybe four issues you might run into that putting your data into some kind of a database, broadly defined, can help you solve. And these are the ones that I like to talk about. So one is sharing data, right? So once you have multiple users trying to access the same pile of data, some sort of infrastructure or interface to manage concurrent access starts to become required. And this is something that I would argue all real databases afford. Okay. Another is, the enforcement of a data model. You might say, well, look, I use a rows and columns data model, or I use a hierarchical data model, but there's some sort of software that needs to enforce that. And so this is something that databases can do. Now remember, the data model is not just the raw structure of parents and children, say, with trees, or rows and columns. It's also higher level constraints, such as this must be a number from 1 to 5, or this must be a day of the week, okay, or it must be one of the customers that already exists in another table. Okay, so these kind of constraints are difficult to enforce in the application layer, and I'll argue this more in a little bit. Okay, so the third reason might be scale, right? So we know we have a pile of data, and we know we have sort of a data model floating around here, but once it gets over a certain size, or we get a certain number of instances of this data model, we're going to want to use specialized algorithms to be able to work with it. And writing all these specialized algorithms ourselves to traverse larger and larger data sets becomes the bottleneck. And so a database can organize these algorithms and expose them through convenient mechanisms. We talk a lot about complexity hiding interfaces, right? Databases provide a complexity hiding interface for large-scale data. And I think the fourth one is flexibility, which is, you might have written some software to access your set of files in a particular way, but as soon as you have to access it in some way you didn't anticipate, right, you have to rewrite a bunch of code. And so what databases try to do is anticipate a broad set of different ways of accessing the data and working with the data, and support all of them. Okay, and so I'm talking pretty abstractly here, fairly deliberately, because all of these things are certainly true of relational databases, which we'll talk about, but I think they ought to be true of anything that sort of earns the term database, and they're certainly true of other systems as well. And so we want to try to keep these things in mind when we think about NoSQL systems and key value stores and graph databases and so on. Okay, so it's not just relational databases. This is broader than just relational databases. All right, and so I think in general, when you're looking at these different systems and thinking about the data storage layer, which is sort of where we're starting here in this conversation about data science, in this course about data science, is how is the data physically organized on disk? What kinds of queries, what kinds of operations are going to be efficiently supported by some particular organization, and what kinds are not, right? So one immediate question, and this third bullet leads to an immediate question: is it hard to update the data or add new data? That's one quick way to split of all the different operations you can do on the data. One quick one is the reads versus the writes. And in many cases, you'll find that what's convenient, the organization that makes sense to read the data efficiently is not the same one that makes it efficient to write the data. And that trade-off is at the heart of a lot of the system design challenges in databases and other large-scale systems. Okay, but there's other kinds of operations as well, as we discussed. Do you want to look up by key? Do you want to look up by some other field, and so on? And we'll talk about this in future segments. Okay. And then what happens if I encounter new queries that I didn't anticipate? Do I need to completely reorganize the data? Do I need to write a bunch of new code? How hard is this? And so this these are the evaluation criteria you're going to use when you're thinking about choosing a platform for your data science task. Okay, or these are some of the questions, or perhaps not all of them, right? So if broadly your choices are a pile of files, an off-the-shelf database, a NoSQL system, or something else, having these questions in mind as you're evaluating the pros and cons is going to be really important, okay? All right.